So, first thing I want to cover today is that today it was disclosed and patched a 23-year-old critical vulnerability in X11 server that allowed root privilege escalation, and it involved scanf and loading a special font that can overflow if carefully crafted. And we'll be covering this, and this is a really, really good demonstration about how old vulnerabilities and things that most people think buffer overflows aren't really a problem, still are problems today and can be critical problems that can own thousands, if not millions, of systems. So, before we jump into that, I want to have a quick little discussion about intro to processors and registers. Really, really brief overview. The motivation for learning C and C security. And we'll cover strings, pointers, and dynamic memory management this time, and finish it all up next time. So the basis of the von Neumann architecture is that you have a processor. You have a region of memory that maybe separate hardware. Then you have input and output, which is likely also separate hardware. And then all these things are communicating over a series of buses. The control bus will have instructions, things that are getting executed. Address will have addresses of data, and then the data bus will have the actual data when it's input and output and being used by the processor. And so the processor itself has a number of registers, or you might think of them as variables, really, that it uses to get things done. And so one of the most important ones is EIP, and we'll cover that next. But for general purpose, EAX, EBX, ECX, and EDX are the main ones with which most computations are done. So 1 plus 1 is probably going to use EAX, EBX, and store it in EAX and stuff like that. Now for accessing like arrays and strings, that's where ESI and EDI come in. ESI stands for source index, and it's really basically, it denotes the source of that array of data or that sequence of characters that is going to be used for the operand. And the EDI basically denotes the destination that we're going to store the results of whatever computation we are performing. So ECX is also standardly used by compilers for various counting operations, and EDX is usually used for some form of data computation results as well. So, but the most important thing is EIP. That's the keys to the castle. Hackers want to hijack this during exploitation as the primary target of exploitation. It is basically used to tell the processor what instruction is up next to be executed. So the processor can begin fetching it, decoding what that instruction is, and then executing it. And if you've taken computer architecture, you should be familiar with at least a 5-stage processor. But we won't cover that in this class. It's just something nice to be familiar with. ESP is the stack pointer, and EBP points to the base of the stack. And we'll cover how the stack operates and how functions are called and how they manipulate the stack pointer and the stack frame, and how that is all used to enable recursion and various different things that we enjoy now today in programming languages. So one main tool that came out late last year, I think, is gcc.godbolt.org that we'll be using for this. It is really awesome. It allows you to visualize how code is being compiled into assembly, and allows you to select your compiler, whether it's GCC variants. I think there's even an ARM one in here, which is awesome. You can set the flags. You can do it without optimizations. You can flip between Intel and AT&T syntax, although Intel syntax is far easier, and everyone knows this better. And you can colorize what source code actually correlates to what assembly code. It is extremely useful for learning assembly, and I'm exposing it to you guys because we will be learning reverse engineering, and this helps you get your feet wet. It's very, very useful, and in your homeworks, you'll probably find it useful for analyzing how things work at the atomic level to find vulnerabilities. and I'll be using it to illustrate how they do. So back to this. The one book that I use to put together these lectures that is supremely useful is Secure Coding in C and C++. It's by a very wise person in its cert, and he's written a series of books, and they're all really good. But this has been awesomely useful for this lecture. So C is one of the most widely used programming languages in the entire world. If you want to use a different language, the backend for that language is probably written in C as well. The Java virtual machine, that's written in C. And the vast majority of popular programming languages borrow from it as well. So the guy who invented it, I think, is way cooler than Steve Jobs. It started in '89, and there's been a number of standards for it. The most recent is C11, but most people still refer to C99. And the guy who invented it, Dennis Ritchie, won a Turing Award, which is one of the highest awards you can win in all of computer science. So it is really used in everything. It is used in almost every operating system, used in almost every embedded system. You're going to find it on planes, trains, missile systems, boats, you name it. It's going to be used to write drivers for firmware, for devices. It's going to be used for libraries, other languages. You really just can't get away from it. Many languages wrap some form of C library with their own language as API or interface to it. But to begin, we'll start with strings, because that's what most people get wrong in C. And a string is really a sequence of characters up to and including the null character terminating it. A string has to have a null character terminating it, otherwise it's going to include everything else in the memory space after it when you start doing any operations with it. And it will usually lead to some sort of segfault or undefined behavior. The length of a string is the length of that sequence of characters up to, not including that final null terminating character. The size is the number of bytes allocated to the array. Often you'll find that arrays are using normal characters that are 1 byte long. So the number of characters in the array is also the number of bytes. But we will discover that for various different encoding schemes, for, say, supporting different character sets, internationalization of languages, characters can be of different sized bytes. And so the length of a string may not equal the size of the string. And that's important to know. And so the count is also basically the number of elements in the array. So the atomic size of a string really depends on the length of the character. A UTF-8 character can range from 1 to 4 bytes depending on the system you use, and a wide character can be between 2 to 4 bytes depending on the system you use. Strings can be narrow, and narrow is typically the normal character size, 1 byte. By definition, car in C, according to the standard, is guaranteed to be 1 byte. Wide characters, that's what 2 to 4 bytes is, and then depending on the implementation, there can, in theory, be multi-byte strings using different types of characters throughout. I can't imagine why you'd want to do it, but I'm sure someone has done it for fun. And let's see. Yes, I have all this. And I was going to, oh, you jumped ahead. Okay, copy. We're going to see how things work and size of and how things are calculated. So for character types, there's almost no difference between well, there should be no difference between car, unsigned car, and signed car in terms of the amount of bits it takes. There will always be 1 byte. WCAR types differ, and also I should note that in general, WCAR, which means wide character, is not meant to be signed or unsigned. And we'll talk about data signedness, I think, in the next lecture. There may be some references to it here in this one. I forget. It's been a lot of slides putting together all this. But what we're going to do is see how this is all playing out. So I have a car X, a signed car Y. Let's just comment out the W car for now. In fact, I'll just remove it. So we'll just work with characters, not wide characters at all. And you'll see that in assembly, when I colorize this, these don't really get much assembly code allocated to them. In fact, at the very beginning of a function, you have what is called the epilogue. It allocates anything it needs to the stack and pushes things as necessary. Here, this is a void function and we're not returning anything. So the compiler has figured out how to just basically do this all in line. And in fact, it could do everything right here pretty much with no code if it was able to determine what size of actually does. But the compilers aren't always that smart. So if you see what the tan line of code that I have the cursor blinking on points to, it's basically moving some sort of keyword pointer, and there's the brackets there, comma 1. So the Intel syntax is you move into the destination, comma, from this source. So the source is a hard-coded value of 1. And what it has done is actually, I misspoke. It does know what size of is. That's right. Size of, I've confused it with string length. I'm sorry. Size of is what's determined at compile time. And so, yeah, scratch what I just said. Size of is determined at compile time. And so the compiler knows the size of characters, unsigned characters, and signed characters. And you can see that it is returning 1 for each of these calls. Got it? Any questions? Sorry for the confusion. Okay. So if we go back to, say, W car, you'll see that it is indeed not 1. It is now 4 bytes long. And so let's do this. You'll see that all of these are actually 4 bytes long. And sometimes not knowing this, I'm going back to the lecture, causes developers to use these things incorrectly. So it's important to know the differences between the various characters out there in order to prevent things like 23-year-old vulnerabilities that lead to critical root privilege escalations in millions of systems. So WCAR-T in Windows typically UTF-16. And so it is 16 bits long. It's thus 2 bytes. Linux typically uses UTF-32. And so it is thus 4 bytes long, hence 32 bits. Size of WCAR-T is usually at least 2 bytes, just so you know. And so, like I said earlier, thus the size of the string will not be the same as the length of the string or the number of characters in it. So there are other ways to take the length of an object other than size of. Size of, just passing it a data type, will return the number of bytes it occupies. Size of a variable will likewise also return the number of bytes that it occupies. String length, however, is calculated at runtime. Size of, like I said, and had to clear up the confusion I created, is calculated at compile time. So if we change this to, instead of size of, if it'll let me do string length, I have to pass it a flag to stop this warning. You will see that it's warning me that there's an invalid conversion here, but this tan code is no longer 1 line of code. In fact, what we're doing is we're setting up some registers and then we're calling a function string length. So this is all going to be calculated in real time. I mean, in runtime. So likewise, for wide characters, there's also WCSLen, if it will return. And that's for wide characters, and there are others that I may not be aware of. So this is from the book that I cited at the very beginning, and I'll have most code examples cited from this as well. This is, I believe, yes, okay. All right. Can we get this bigger? All right, so what I wanted to show is that I have 3 strings declared, and maybe I can make this bigger. Oh, that's not working. We'll have to work with that. Sorry. So what I have is, I'll uncolor it for now so it's easier to read. I have 3 strings declared. They're all the same string, okay? But one is assigned, one is signed, one is unsigned, and one is regular. They all are, in fact, doing the roughly same thing when I'm calling string length. Oh, I have stir size ofs here. Move absolute value, call stir length. And this is getting pushed. Colorize. I clicked it. Sometimes it's not working. But this was an example to show that basically how this is being used differently. And I believe I've already illustrated that. Unfortunately, it's not colorizing at the moment. But the lesson here is to properly calculate the correct string length and use the proper character functions to do that. So the next set of functions, there's a wide family of them. Some of them vary from the C99 standard to non-standard ones that maybe are part of POSIX standards or part of Windows API or libraries. And the main ones in the C standard are memcopy, memmove, strcopy, and stringcopy. And these lecture slides, which are available on the website, I have it so that when you click on a link, it'll take you to the manual for that function. And that will help you guys out in your homework. So some of these are more safe than others, but even the safe functions can be used improperly. And so it's important to always, for developers, to always know how to safely use a safe function. So function like strcopy is an unsafe function that copies an unbounded amount of characters into a destination. It keeps reading until it finds a null terminating character. If the source is not properly null terminating, it's going to keep reading up until it finds a 0 by the null terminator. And so if you put too much information into too small of a space, that's classically defined as a buffer overflow. If you calculate the number of characters wrong, that can also use it in a safe function, that can also lead to a buffer overflow as well. And so there are other ways to cause buffer overflows and using concatenation functions, some of which can also be used for just string copying, like sprintf and snprintf, allow you to concatenate 2 strings together, or perhaps in a formatted manner for the format string functions. And so let's cover some common errors. This is, if you're hoping for like intro to C class, this is definitely not that. This is intro to breaking C and finding ways C is broken. You don't necessarily need advanced programming concepts under your belt in order to find vulnerabilities and bugs. That's what I'm going with. You don't need all the theory. You just need the techniques and understanding how, when these things are used wrong, how to find them and how they manifest. And it allows you to think this way and find much more, even outside of C and what's limitedly covered in this lecture. So the above common errors all mostly lead to the thing called undefined behavior. Undefined behavior is basically a confusing arena of activity or behaviors that the compiler developers just didn't want to deal with. They basically reasoned that in these cases, no one should logically ever cause this behavior, so we're not going to come up with all the constraints and protections to protect against it. Like 1 divided by 0, right? Who's ever going to need to do that? That shouldn't be valid. So in many cases, undefined behavior potentially causes memory corruption. And that is a superset of bug cases that usually you will find memory system vulnerabilities in. And so that's what we're going to focus on. So improperly bound to string copies, the culprits of old are really getS, which can never be used safely. Stir copy, which can actually be used safely if the source string is something that's statically defined in the source code, like car 10 equals hello, null terminate. That's a static string, and if it's declared in the source code and not increased, it's going to be used safely in the stir copy if the destination is big enough. The newer common culprits of buffer overflows are the safe string copy, memmove, memcopy, sprintf, snprintf, and others. I should have put a ... but getS, this is the source code for it. It basically keeps reading. It takes in the destination. It uses the standard in as the source, and that's what getCar is providing. And then it uses a character pointer to indicate the first character at the destination. And then what it's doing is it's incrementing that character pointer and reading in the character, and then getting the next character, and iteratively going so on, so on, so on. And so what it's doing is it's doing this until it reads end of file, which is also a null character, 0, 0, or a new line. And then it null terminates at the end. And what happens is that this can never be used safely because it doesn't care what the size of the destination is. So you can always overflow it if you so choose. So this is a basic example of how unsafe stir copy would be, rather academic, rather trivial. Basically, all you need to do is provide an input string greater than 256 characters. Makes sense. So a safe use would be for string copy, it takes in the first input is the destination, second input is the source or the input, and you should use the size. Then the next parameter is the number of characters to write. Well, it should be the number of characters that are in the destination. If you use the number of characters that are in the source, if it's greater, you're going to write more than is the destination into the destination. Make sense? So using the length of the input is actually incorrect. So this is also vulnerable. And all you have to do is pass it something more than 256 characters. So another improperly bounded string copy would be sprintf. This is unbounded formatted copy into buffer. Rather straightforward. And off by one error is usually involve reading and writing outside the bounds of the array. So say you have like a character of 10, and you're iterating in a for loop. You declare I equals 0. And you're doing something to each little character, and your bound is not less than 10, it's less than or equal to 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is actually going to be, including the 0, is going to be 11 characters. I started counting on one of my fingers. This is an example of, say, very trivial, an improper bound. You'll find that S1 is 9 characters long, and it keeps going to the 10th. So it'll write the null byte, actually, and it will write two characters past that, or a character past that, rather. And that can corrupt what is on the stack before that, and you will find as we explore how the stack operates, that will actually overwrite a byte of the return address if there's no cookie padding it. So string truncation really only is a vulnerability depending on application logic. Perhaps when warnings on how to safely use things get cut off. And this really only happens when you safely put too much information into too small of a space. So that stuff gets safely cut off, right? It's pretty trivial to understand. So null termination errors occur when developers assume that some of these functions will null terminate their results for them. In many cases, they don't actually. Even the safe ones like string copy, snprintf, and string cat won't actually append a null byte onto the end of the result. So failure to account for that can lead to buffer overflows and memory corruption. So mitigations involve following, this is a fantastic resource for understanding all the different character sets out there, UTF-8, UTF-16, UTF-32, and the different character sets. I found in my work that well, no, it was on NetSeg, that certain Chinese character sets, if a website is using them, will cause most of Firefox and most of Chrome versions to just completely crash if a website's hosting it. So that was really interesting to see. And so sometimes the browsers just don't even support it, just like bad data. I forget what the HTTP code is. And so the other thing is there are compiler flags to warn you of unsafe function handling and that you should use functions safely. But there's another thing that protects memory corruptions from actually manifesting into vulnerabilities. And underscore fortify underscore source is what generates stack cookies, at least for the GCC compiler. I believe it's also for the Microsoft C++ compiler. And so we'll cover cookies in about a month from now. So you don't have to know that right now. So now let's cover the next most misunderstood thing in C, in most of computer science, is how to safely use pointers. Pointers are actually quite easy. It's just a lot of people have problems with them. So let's cover how to do pointers. So these things, when you see them. So when you declare, you use the asterisk, this declarative operator. It instantiates a variable pointing to an object of the given type. So if you just have car star x, right? It's going to tell the compiler that I have a pointer pointing to a character object. It may contain a number of characters, not just one. And so for wcar underscore t, it's pointing to a wide character style object, and so on for the last example. And so those alone are going to be undeclared. And so if you use them without instantiating them or assigning them a value, they're not actually going to be null, and you shouldn't assume they're going to be null. They're going to be what is ever in memory, and memory may not be zeroed out. So if you use uninitialized variables, it leads to undefined behavior. Well, it is undefined behavior. Let's see. It can lead to a vulnerability if you use it, say, as a function pointer, right? And you use it after some sets of checks, and you fail to check one case, and you end up using it without declaring it. Well, if I'm able to fill that region of memory where you're perhaps using it with a pointer to some malicious code, you will instead execute my pointer without setting it to whatever you wanted. And you'll probably see that later in this class. So when you use it as an operator, not in declaration, it's a dereference operator, and it denotes indirection. So this is a better way to think of it. When you just use x as if it's declared as a pointer, it will show you the address of the target. but if you use the asterisk operator to dereference it, it will show you the value of the target, okay? And so if you use it as an operator on a null pointer, it will typically trigger a segfault trying to dereference 00000 and point at the value there. Usually you won't have memory permissions there. But if it is a memory mappable address, you do have memory permissions, like in many old school systems and most modern embedded systems. This is a vulnerability. And actually, null pointer is the name of the CTF club that I founded. Null, N-O-L-E, as in FSG Seminoles, but also sounds like null. Just is one of those rare cases where a CTF team actually manages to match their actual school, unlike 99% of them. So yeah, this diagram is the best way to think of it. And when you see the ampersand, it instructs the compiler to print or use the address of the pointer. Not the address that the pointer points to, but the address of the pointer. So using ampersand in this manner, for this, we'll actually use the address here, and if you run this print statement in some given code, it will behave accordingly. So ampersand x will print out the address of this character pointer, x will print out the address of the target, asterisk x will print out A, B, C, D. All right? Okay. So there's another way to use pointers, and the arrow operand dereferences a structure and accesses a member of that structure. So think of like linked lists. You use p.next for a structure that has a forward or next pointer and perhaps a back pointer, or a struct that say has a name string or a character pointer that points to the string somewhere. So that's how that would work. And so array indexing is the last one we'll cover. And so basically x sub y returns the yth element of x and is exactly equivalent to basically doing asterisk of the expression provided there. I'm not going to read it out because all the parentheses. And so also while we're at it, the member of operator is functionally equivalent to this formula here. And so that's just useful for your understanding. I'm not going to have you regurgitate this exactly on a test. I'm not that kind of guy. So function pointers are where vulnerabilities often arise more often than other classes of pointer bugs because these get executed. If you manage to replace a function pointer with a malicious address to your malicious code, and it gets executed, your malicious code is going to get executed. The processor doesn't know any better, it doesn't care. So they must be handled more carefully than others. This is an example of what these things assemble to. And the blue and green code is calling the exact same function, good function, just a different way. The first one, the blue, is calling it via function pointer. And so you see the function pointer is declared here, static void function pointer. It takes in constant character pointer. And after it's declared, it's instantiated. The function pointer is given the address of good function, right? And then void may not even be necessary, but basically it dereferences function pointer to go to function pointer and then passes it the value high. And so what this is doing is, to see how this is just different, it's really just different by about one line of assembly. You see in both that they have this line in common, the move into EDI this, all right? So what it's doing is it's setting up a parameter to be passed to the function. And in this case, EDI is where it's expecting the string parameter to be located, the first index of that array, and then it starts using it iteratively. All right? Now, when it's declaring the function pointer, however, you see at the very end, the difference here is it calls RAX. RAX is the 64-bit version of EAX. you'll find that 32-bit versions all start with EAX, EBX, ECX, EDX. When they moved to the 64-bit architecture, they started appending everything with R instead of E. I don't know why. I don't really care why. So RAX is the 64-bit version of EAX. So it calls a 64-bit pointer stored in RAX, and in the latter version, this green, it just simply calls good function, and the compiler supplies it with that address at basic compile time. Well, the assembler does, rather. And so you see that RAX is calculated here, and it's used as basically some sort of offset from some base. And we'll cover that later, probably. So this is an example of how a pointer would probably be used in error. Both of these actually will compile and will run, but you see they don't really do anything. So there's no real logical errors that can result from incorrectly calculating what dest is. But you see the difference is that what they're doing is they have this string, they have some sort of destination, right? And they're basically mallocing a chunk of memory that's equal to the string length of that given string. And I guess they'll probably use it later for some sort of operation to store the destination of something, right? So what we're going to see is that if you remember, the size of car is going to be 1, and the size of car star, however, is going to be a pointer pointing to an object of size car. So how does that manifest in memory once it's assembled? Is it going to be the same size as car? Is it going to be different? Is car going to be the same size as a pointer is effectively what I'm asking. And so what we'll find is that on a 64-bit system, you'll have this being 64 bits being used. This is, however, 8 bits, 1 byte. Now, a 32-bit system is obviously going to be 32 bits, it's going to be 4 bytes, right? Okay. So if you use this, because what malloc is returning is a pointer. If you use only 8 bits to address something in memory, you're going to have a problem on either a 32-bit system or a 64-bit system. It's going to keep reading the next 32 minus 8 or 64 minus 8 bits past that one little byte and use it as part of the address. And that can point anywhere. And if you're able to populate that memory, because it's being used in an improperly instantiated way, you can perhaps hijack it to point to malicious code. So let's see exactly how this manifests in assembly. And so the purple here correlates to the purple here. And this is going to move, since it's being used properly, and we have it declared as a character pointer, okay? It's going to move 8 bytes to the destination. And it's important to note that if you see something like minus 8 here, that has nothing to do with the 8 bytes that are being moved. That's simply just in reference to the base pointer for the stack frame. So what is going on is, oh, I should have done size of. Oh, well. Oh, right. See, it moves RAX into this. Now, if we just move the car, it's going to move AL. Do I have? Let's go to the very beginning. So you can see the difference between RAX and AL. Go to the beginning. Okay. All right, so this is for 32-bit systems. And what we have is that back with just 32-bit systems, there are a number of different ways to call a single register. If you call EAX and use it, it uses all 32 bits of that register. If you call AX, it only uses the lower 16 bits, the lower half of that register. If you call AL, it only uses the lower byte, the lower 8 bits of that register. So you see the differences between those two was that it was moving RAX, which is going to be 64 bits. And then when it's improperly used, it was moving AL, which is only 8 bits. So AH or BH or CH moves the upper 8 bits of the lower 16 bits, right, I know, a little confusing, into whatever you're using it. And so I tried to find a diagram with RAX in 64 bits, but I was unable to at the time. So back to slide 45. Okay, and so we see AL is being moved. So it's only going to be using 8 bits of the result of malloc. So that can be used in the improper use of pointers. So another important, yes?
I have a question. The assembly code that shows, that's not position-independent executable being built, right?
I don't believe so.
Does the site that generates that, does that have position-independent executable assembly set?
You know, I don't know. I haven't toyed around with it that much. It's really useful for, visualizing this much. I haven't toyed around with how well it's able to colorize complex things that are being like inlined and stuff like that by optimization. And so I haven't also toyed around with position independence. But I think you should be able to turn off various different protections, and I'm not sure if there's a protection to. It depends on the compiler. Some compilers may support ASLR flags to disable ASLR, which would make things less random, and there may be other flags to do this. I'm not sure. I'm not a compilers expert. On a scale of 1 to 10 for compilers, probably 2 or 3. Actually, just better reverse engineering and breaking stuff. So, Windows and Linux use a similar technique for linking and transferring control of a library, of a process to a library function. The important thing to note is Linux's implementation is exploitable, while Windows is as far as we know, is safe. So as part of the executable and linking format, which is the corresponding format to .exe in Linux land, you're not going to see files .exe or .elf in Linux. It doesn't use the suffix or the dot suffix of a file to figure out what type of file it is. So there's a section of binaries in the ELF format called the global offset table. And it holds the absolute addresses of various things. And this is essential for dynamically linked libraries. So every function used by a program has a global offset table entry. And that contains the actual address of the function. When you first call it, it may reference the GOT, and the GOT may have nothing for it, or it may have to go look it up. And so before the first use of the library function, the GOT entry points to the runtime linker, all right? And so this is what I said, that the runtime linker is then passed control, and its job is to find the real address for the target function and insert it into the global offset table. And so that next time the global offset table is used to find this function, it doesn't have to go to the runtime linker. It's already populated and it's good to go. So the problem here is the global offset table is located at a fixed address in every single ELF. And so because the runtime linker at runtime has to modify that segment, it is not write protected, which means that because it's not so fine-grained that only the runtime linker can write to it, anyone can write to it. So if you can cause an arbitrary write to that address of memory, you can overwrite a value in the global offset table. So if something hasn't been used for the first time, or if it has been used for the first time, and you can still overwrite that value in the global offset table, when that function is used next, you can point to a different segment of code. As long as you point to something that has executable permissions. And we'll cover memory segment permissions in a little bit. probably reverse engineering week. So that's the basic gist of global offset table exploitation. And you can learn more about how this all works with a tool called object dump in Linux. There's also the detour section. It's for deconstructors. It's really only with the GCC compiler. But it contains the function pointer to the destructor. And the destructor usually runs after everything else has run and is done, is doing garbage collection. The constructor, however, runs before most things run. And also runs before most programs get a chance to interact with anything, to interact with the user, or to interact with a hacker or a malicious user. And so the CTORs really isn't targeted ever. However, if you can, like the GOT, if you can overwrite it, you can overwrite function pointers that are being used at the very end of the program. So that's one area that you can target to hijack execution. So that's the end of our pointer coverage. And we'll have more on that in exploitation as we get to it. We need to cover now dynamic memory management. What time is it? Oh wow, we got plenty of time. I'm going really fast. So we're going to cover the C memory management model, all right? And we're going to cover some common errors. And if we get to it, I'll probably cover Doug Lee's memory allocator, and maybe if we get to it, a double-free vulnerability. We will see. I'm ahead of schedule. So the C99 standard provides 4 memory allocation functions, all right? malloc, if you've seen C, you've seen malloc. You should be pretty familiar with it. Aligned alloc, it's pretty rare. Most people don't see it. Realloc is actually quite common, and calloc is quite common too. So malloc basically takes in size and returns a pointer to a memory address of that size, if it's able to allocate it. Aligned alloc allocates the same thing, but has an alignment specifier, and I'll cover alignment next. It's an old term that's mostly not very consequential anymore, but back in the day meant the difference between your program running or not. Realloc changes the size of a memory pointed to by pointer P to be of a different size, either greater or smaller. The contents up to that point will be unchanged. The remainder, if you're cutting out some size, will be attempted to be freed, in which case, if you reuse it without initializing it or zeroing it, it will have the old value still in there. So calloc allocates basically a number of elements of size t and returns a pointer to the allocated memory. That memory is set to 0. So that is one that actually does zero out a segment of memory. So alignment was usually a processor design requirement back in the 90s and before. And on most early Unix systems, an attempt to use misaligned data would crash the system. And so what it needed was for things that were 8 bits long to start an address that is, well, start in any address. But if it's 2 bytes long, it has to start an address that's a multiple of 2 bytes. If it's 8 bytes long, it has to start an address that's a multiple of 8 bytes. And so on and so on. So if you had an 8-byte object aligned on something that's a multiple of 7 bytes, but not 8, it would cause the processor to fall over, basically. It would crash the process. Modern systems support this and don't really care. The compiler usually avoids it, but if it does encounter this, it usually just impacts performance in some shape or fashion. However, this is important for exploitation. In some cases, you'll find that your exploit's almost there, and you just have to align it right on the stack. And we'll get into that. So this is basically what I said, that objects have to lie in neatly aligned byte slots. And it doesn't matter what order they are, as long as they are done in this fashion. So all of memory is outlined, and for like this sort of system, a D word is going to be 4 bytes, Q word is going to be 8 bytes, and then byte is just going to be 1 byte. Have to be in such a fashion. So, any questions? It's pretty simple. So, an interesting thing is this is not a C99 standard, but there is a dynamic memory allocation function, alloc_a, that uses a stack for dynamic memory allocation and can thus stack overflow. It should be noted that the ones covered up until this point, these 4 functions use the heap. The heap is the primary memory segment for dynamic memory management and allocation. The stack is primarily used for things that are already declared beforehand. I need a character array of size 10. But for the heap, I'm taking user input. I don't know how much, so I'm going to take it in, and I'm going to work with it accordingly, depending on what happens at runtime. That's where operations will be typically occurring on the heap. So let's cover some basic memory management errors. So failure to initialize, or basically means failure to zero out memory and use it assuming that something else has zeroed it out. People also sometimes assume that free will zero memory. That is not the case. And if they reuse it, they can reuse potentially malicious stuff if it can be poked at by attackers, perhaps via heap spray. But that will be covered a bit later. And then failure to check return values. These functions can return error codes, and if you just use it and assume it's good, in the one case that perhaps the heap doesn't have any more memory to allocate, and you try using it, you can lead to memory corruption, lead to undefined behavior. The process will fall apart. So it's important to check the return codes of these functions in almost every function. That's the lesson of this slide. Using freed memory, it is basically possible to access a memory that's been freed unless all the pointers to it. Wait, what am I saying? What did I say on this slide? Right. Unless you null out all the pointers, it's still possible to access memory that's been freed. So you have 2 pointers that point to the same thing, you call free on one of them. But the other one's still going to be fine, all right? And if you use it, well, it's not going to be fine. If you end up using the other one, perhaps by programmer error, right? It will lead to undefined behavior. It's using freed up memory, and it can cause vulnerabilities. So this is an example. Let's see if okay. So this is an example of dereferencing a pointer after it's been freed. So what that's going to do is this loop sets P to the head of a linked list. And so as long as the pointer is not null, it keeps going along the list and freeing that value. So the first thing it's going to do is it's going to free P, but the next line of code that's logically going to execute is going to be set P equal to P, which has been freed, sub next. So this dereferences something that's been freed, and it's not safe. So the safer way to do this is to use 2 pointers, so temporary one, and go about it this way. Does it make sense? Anyone have any questions? Okay. So logically what this is going to do is going to call the first free on P, and it's going to set P equal to Q. Q is going to be fine, all right? Q's going to then it could be set to Q sub next or P sub next. That's inconsequential. However, this is now being done and calculated safely. That's what's important. So let's see. not all examples of this bug work like that on like a linked list. Multiple frees on the same memory. Say you have a developer who copy and pastes a lot and doesn't do object-oriented coding well. And you'll see a code chunk be like x equals malloc n times size of int, do a lot of stuff, and then freed it, at the end. And then you copied that segment, pasted it, and did more code. But then in the end forgot to change this. Well, that's freeing up the same memory twice, and that is a bug. Can cause seg fault, can cause vulnerability, depending on what happens. So common causes really are cut and paste errors, sloppy error handling, and it can result in corrupting the heap memory manager. And we'll cover the memory manager for the heap and how it works in general, either today or next time. And it can also cause memory leaks and info leaks, and not info leaks, but rather can cause, depending on what happens, if it happens at initialization time. A lot of games suffer optimization problems and double free problems that lead to memory leaks and lead to things, if they keep getting called and keep doing this, keep eating up memory and slowly growing. And it becomes slower and slower and slower and slower. So, yes, basically, this is exactly what I was saying. I should just went to the next slide. So yeah, memory leaks. So the memory allocator on most systems runs as part of the process. The compiler adds in code, adds in code to do this, and is usually provided to the linker by the operating system. So each operating system typically has its own memory manager. However, compilers can provide directives to override it, perhaps provide an alternative one if the developer thinks this alternative one is safer, which in many cases there are safer linkers, or safer memory managers, sorry. And it can be linked in statically or dynamically. Does anyone not know the difference between static linking and dynamic linking? Don't hesitate to raise your hand. I see some blank faces. So I'm just going to go ahead and cover it. So if you statically link a program, as opposed to dynamically link a program, dynamically link means that when you compile it, all right, all those function libraries, standard in, standard IO, standard lib, right? Those are going to be brought in at runtime. So the binary that you compile, that resulting program, doesn't have all that code in there. So the file size is much smaller. And so most things you will find on Linux systems are dynamically compiled to keep things small. If you statically compile something, it loads the libraries in and puts all the libraries that is going to be used into the binary, resulting in a much higher size file. However, what that means is that you can take it to another system that may not have the exact same libraries, but you'll know it'll at least still work. In the majority of the cases, as long as the system calls for the operating system align and are used the same way. So, in general, a memory allocator requires a maintained list of free available memory. Oops. Back. So you have a list of the freed memory that you can work with, that you can allocate to be used. And then an algorithm to allocate a contiguous chunk of memory of n given bytes. And there are two general algorithms. There's the best fit method and the first fit method. The best fit method is really, it just takes a chunk, the smallest chunk m, that's greater than or equal to the size n that it can find, and it uses it for the job. All right. The first fit is it uses the first thing it finds, and it's the fastest, but not the best user of size. It doesn't use it efficiently. So, and then you need, thirdly, algorithm to deallocate said chunks, in essence, to free them. All right. So what you do is basically you take that chunk and you return it to the free list. All right. So common optimization includes chunk boundary tags. It's basically metadata. So think of the free list like a list of chunks, okay? And it's like a linked list. One points to the next. And so some of these tags can include the size of this chunk and the size of the last chunk to enable certain algorithm optimizations. And the main algorithms you have to optimize are the allocate algorithm and the free algorithm. These are basic data structures in computer science. And so it's common for tag to contain the size of the current chunk, a pointer to the next chunk, and a pointer to the previous chunk, like a doubly linked list. This is the end of this lecture, but we still have about 20 minutes. So I'm going to go with the conclusion of this and then just go ahead and start the next lecture, because I already have the slides prepared. Well, actually, I'll probably just stop here for now and open up for any questions. And if we want to keep going, we'll keep going. So in the next lecture, we're going to pick up, if we start it, the rest of dynamic memory and cover integers and runtime stuff and other stuff. But the concluding mitigations for the topics covered in these slides are the pointers. It's important to use. It's useful to use fortify source to add stack canaries. It's useful to use NX and dep, and we'll cover that later. There's also, I don't feel like talking about encoding and decoding function pointers. For strings, there's a good recommendation by the author of the book that I use to have a unified string model for handling allocation and freeing for just strings and dynamic memory in general. And as long as you're consistent across the board, the general lesson is that you should be fine, as long as you fit into one of these three approaches. So, including mitigations for dynamic memory is that nullify pointers after freeing them. Free does not set the pointer to null. It does not also zero out the memory either. ASLR is important, and we'll cover that later. And testing is really good. Valgrind, Ensure++, Microsoft's Application Verifier, and I've heard good things about IBM's Purify. I haven't had the chance to use it. That is today's reading. It's very relevant. Should be about 30 pages or so. Not too bad. If you don't have the textbook yet, does anyone not have the textbook yet? Okay. It is on No Starch Press's website. I can pass around the book again if I have it on me. Or it just looks like this. Hacking, the Art of Exploitation. So OX260 refers to Chapter 2, Section 6. So let's see. Sure, Google. All right. Well, you can usually find it cheaper than $50. Amazon should have some used copies and others. And you don't have to have the print book. The ebook, PDF, is available if you have to have it now. The live CD, any codec service from the book you can download. Also, the live CD can be torrented from the publisher, and I'll provide instructions, and if we use this, we probably will, or something else, hopefully within the next 2 weeks. But class-wise, what we've covered so far is the intro. So if you just came in late and you didn't attend Monday's class, the videotape for Monday's lecture is up on the website. You're responsible for watching it. And then I'll upload today's lecture as well. Homework 1 is out. And today after class, I will be emailing out the website so everyone has it and doesn't have to write it down. But if you have to find it and you don't know the URL off the top of your head, just type in Owen Redwood, FSU. You find my personal page. It's going to be one of the first links under the courses taught. So that should be pretty easy. But yeah, who wants to keep going or who wants to end 9 minutes early? Keep going. 1, 2, 3, 4, 5, 6, 7. Who wants to go? We're going to keep going. Okay. All right. All right, so we're going to continue the discussion while it's still fresh on in your brains, and just get through the dynamic memory discussion. Maybe not up to the vulnerability discussion, but like I said, it's the linker adds in code usually provided by the OS. The compiler can override the choice. It can be put in there dynamically or statically. There's basically 3 parts to it: the list of free available chunks, algorithm to allocate a chunk, algorithm to deallocate or free a chunk. And then there's metadata usually in each chunk: the size of the current chunk, pointer to the next chunk, pointer to the previous chunk. And so the basis of the Linux memory allocator is that free chunks are arranged in a doubly linked list. It's a circular doubly linked list, so it points all the way back to the beginning at the end of it. And each chunk, both used and free, has a pointer to the next chunk and the previous chunk, and the size of the previous chunk, and the last 4 bytes of the previous chunk if not free. This is a mystery to me. I'm not going to ask you this. It's just something in the algorithm. I've read a lot of things. I don't understand it yet. So if I don't understand it, I'm not going to ask you to understand it. If you happen to understand it, I'd love to talk to you. And then lastly, the last thing each chunk's metadata has is a flag for the previous chunk if used or free. Now this flag is usually packed into a other slot and is just used as 1 bit. So there's a little trick they did to get that to work. So this was what the P is. All right. And so what they did is that sizes of each chunk have to be even. And so what describes whether or not something is even or odd is the least significant bit, all right? And so since everything's going to be even, it's always going to be 0, all right? So they decided to just like, well, we know the size is always going to have least significant bit 0, so let's use that for something useful, all right? So that bit is what denotes whether or not the previous chunk is in use or if it's free. And that's used in an algorithm that we'll explore. So the chunk boundaries, I have chunk 1 listed here, chunk 2 listed here, all right, are basically starts here, ends here. And so on the left we have allocated chunks, on the right we have an example of a freed one. So an allocated chunk, this is where all the data is, all right? And so when you do alloc, say, of size n, it's going to allocate n here, but you see we have other data, describing this chunk. So the size of this bin is actually going to be larger than whatever we allocate in all cases, all right? So you're going to have an integer for the size of the last chunk, integer for size of this chunk, and so on. In the free chunk, it just uses what is going to be the data for its other purposes. All right, so that's more or less inconsequential. So let's talk about the allocator, because that takes things from the free chunks, doubly linked circular list, and unlinks it and provides it to the user to be operated with. So each doubly linked list consists of forward pointers and backward pointers. The very end points all the way back to the beginning. And so it's going to look like this. And so let's explore how unlinking works. Can everyone see that? Okay, just want to make sure. So the unlinking algorithm is really just 4 steps. It takes in a given pointer to a block, pointer to be used really for backwards, and a pointer to be used for forwards. They don't have to be defined beforehand, but P does. Okay? So on the left, we have a list of free chunks, and on the right, we have the allocated chunks. And so let's say this is P, this chunk, okay? The first thing that's going to happen is we're going to set the forward pointer equal to the current chunk's next pointer. So we take this data that's located in P, and we find out where it's pointing the next chunk is, and we set this to be our temporary value for FD. And we do the same for B, K. And so these green arrows, if you can see them, are basically illustrating what these are being populated with. So forward is pointing down here to the next one. Back is pointing all the way back to the beginning of the previous chunk. And this is where the swap happens. It's taking the back pointer at the given next chunk, and remember how we said that this, when you use it in assembly, it takes the very first index and accesses it by an offset. So this struct has this offset for the back pointer, and it's setting the back pointer to be what is temporarily being used as the previous chunk to P. So what this is doing is it's taking this back pointer in the next chunk and saying, now your previous chunk is the one before me because I'm going away to be used. Make sense? All right. And so accordingly, the previous chunk's forward pointer is set to be the next chunk for the current one. And thus it is completely unlinked. And so it's done, it can now be allocated, and it can be used. So 2 things to note. 2 pointers here are changed, all right? The forward pointer and the backwards pointer. This is very, very important to keep in mind because the system trusts the data that's in this chunk to do this right. What if that data is maliciously provided? It's relying on this to do 2 things, to find the next pointer and to give it a value to that pointer. So we're providing, if you can do this maliciously, a destination for an arbitrary byte and value for an arbitrary byte. And so let's put that on the back burner for next time. Class is about over, and we'll pick up here. And free is roughly the reverse of this process. And that'll be it for today's class.